customers are removing 2 or more RDR-4000 components, or LRUs, for some of the fault codes that they're seeing on the RP1 display. And that leads to, when the units are sent to our service facilities, 1 confirmed component removal, but 1 or more additional components are found to be no fault found, NFF. This webinar is associated with a service information letter that was just published in order to address this issue. The 4000 is a revolution in radar technology for both the air transport and business jet market. The system was introduced to the air transport market in its federated, as it's called, state approximately in 2011. It's the first and only radar system in our markets to introduce pulse compression as well as a 3-dimensional volumetric buffer memory to these markets at an affordable price. The system's capable of presenting weather reflectivity data, turbulence data associated with rainfall, and forward-looking predictive wind shear data, terrain mapping data, and lightning and hail indications. The system consists of a radar processor known as the RP1, which is the heart of the system, a transmitter receiver known as the TR1, which is mounted in the radome, the antenna pedestal, antenna arrays. For all air transport, we use a 30-inch antenna called FP30-1. And then for the BizJet market, usually either a 24-inch or an 18-inch. And there are several different control panels. There's a CP1A for a single system, CP1B for dual system, and then for Airbus configurations, a CP2B. This is a simplified schematic as an overview of the 4000 system. The heart of the system is the RP1 processor, which is mounted in the electronics bay of the typical aircraft. The RP1 is where you have your main control software, your BITE, built-in test equipment software, monitoring the entire system, and also the main power supply, which receives in air transport 115 volts AC from the aircraft, or on the BizJet versions, plus 28 volts DC. The power supply module inside the radar processor block diagram provides its own internal voltages. It provides plus 28 volts for the external control panel, and it provides power to the TR1 and DA1 antenna drive units, which are mounted inside the radome at the front of the aircraft. It provides the power by means of a plus 200 volt line to those units. The RP1 interfaces with several other systems in the aircraft. You can see the signals on the right side. It has ARINC 453 display interface for the EFIS system, EFIS display system. And the business jet aircraft, like a Gulfstream 650, we provide that display via Ethernet. Since this is a predictive wind shear radar system, we also provide audio output for the wind shear caution and warning sounds, lamp drivers for the EFIS system for wind shear caution and warning alerts. And we also need to interface with the EGPWS system. We also need to interface with the air data computer for barometric altitude, for our volumetric buffer processing, as well as attitude inputs like pitch, roll, magnetic heading, and ground speed. And we need the radio altimeter, very similar to the TCAS system, for the trip altitudes to determine whether we should be beginning or ending the predictive wind shear processing based on altitude. We also use flight management system data. This is to determine whether the weather in front of the aircraft is either relevant or irrelevant weather based on whether we have the mode in the automatic weather mode. If we go to the manual weather mode, then we don't need the FMS data. And some of the aircraft configurations are now interfacing to the ACARS CMU, where we can download status data from the weather radar to the ACARS system. Internal connections, system internal connections between the components. The RP1 is connected to the TR1, not only in power, but by means of ARINC-429, we provide controls for the transmitter and antenna function. We also give byte commands to check the health of the system, and we can receive confirmation data both for the control and for the byte from the TR1. The transmitter receiver units are mounted in the bottom of the DA1 pedestal, which is mounted on the bulkhead inside the radar. The TR1 has a controller card that constantly is in communications with the server controller of the RP1. And under those commands, it knows when to go into the weather mode, map mode, whether to start the wind shear processing. Internal in the TR1, there is a synthesizer, and we increase the frequencies until we achieve the operating frequency band of 9335 to 9375 megahertz. Then that is sent to the transmitter for the final output, which is a pulse compressed signal with a power level of nominal 40 watts. That is sent then through the waveguide to the FP30 flat plate. We emit the energy to the weather systems, weather cells, or in ground map mode terrain data. Reflectivity data is sent back through the antenna, through the waveguide, to the down converter inside the TR1 module, and then we down convert the 9335 to 9375 megahertz to a much more manageable 48 megahertz IF. We send that 48 megahertz IF signal back to the RP1 for digital signal, analog to digital conversion, and then digital signal processing. Now, in order to do the analog to digital conversion and for communications purposes, the second critical signal between the TR1 and the RP1 is a signal called clock, or T0 clock. And it's a BPSK modulated 64 megahertz carrier. And again, that is used as a master clock from the TR1 in order for the digital signal processing internal to the RP1 to convert the 48 megahertz IF into the radar process signal that we're going to prepare for the 3D buffer, and then finally for the display system. And then finally at the top, another job of the TR1 is to control the antenna. So by means of an internal RS-422 connection between the TR1 and what is called the gimbal drive module, or DDM, which is internal in a shielded area inside the DA1 antenna pedestal, we create the commands to drive the elevation and azimuth motors, and then tied to those motors, we have resolvers, which moment to moment show us the position of the antenna in both the azimuth and elevation. Then we transfer that data from the GDM module to the TR1, and then the TR1 on ARINC-429 back to the RP1. So at every moment, the RP1 knows that it gave the command for the antenna position to the TR1, and we have confirmation that everything is working correctly. This is the front panel of the RP1. Notice you have an LCD display and you have two push buttons just below the display. Those buttons, as you walk through a menu, their functions constantly change depending where you are in the menu. And this particular snapshot, notice you can see a number 3049, which happens to be a recorded or a logged fault code that we'll be talking about shortly. But it is when we talk about the fault codes, it's the RP1 where you can see it in decimal format. In the Airbus aircraft, we can also see these fault codes, but there is a hexadecimal equivalent called the TSD code that's associated with these same codes. And now we start the fault tables. These tables are taken from the new service information letter that I'll be mentioning at the end of the webinar. Again, these fault codes are in the line maintenance manuals. There are 3 line maintenance manuals for this system, one for Boeing, one for Airbus, and one for business jets. We're in the process of clarifying the fault codes in those manuals as well, but we do have the guidance from the service letter. This first slide covers all the fault codes that are associated with the 48 megahertz IF failures. And the first code is the 3049 that we saw on the front panel of the LCD of the RP1. And the name of the fault, IF cable, from the TR to the RP, 48 megahertz IF. And you notice just to the left of the fault code, there's Airbus TSD code, troubleshooting data code. That's in hexadecimal, 0BE9. Where the Airbus customer would see this is on a printout from the CFDS. If there are any faults in the radar system, it would show the TSD codes. If I receive a 3049 code, the first recommended action is remove the RP. It's probably the RP more than likely is the fault. If the RP does not solve the problem, then it's probably a problem with the 48 megahertz IF cable itself between the TR1 and the RP1. They need to replace that. And we've had many issues with both the IF and the clock cable. For one reason or another, more issues with the business jet like the 650, but it has been a problem. The next code, 3057, is almost exactly like the 3049 code. The same recommended action is to replace first the RP1, and if that doesn't solve the problem, then replace the 48 megahertz IF cable. Now, if we receive a 3049 code, and at the same time, in the same fault leg, we also show a 5051 code, then the TR is more than likely the fault, not the RP1. And again, that's if there's a 3049 code, but associated with 5051. And the same idea, the last one, 3057, very similar to the 3049. And again, if it's associated in the same flight leg with the 5051 code, the action would be to replace the TR. Okay, the next group of faults is associated with the 64 megahertz clock and RS-422 faults associated with the DA1 antenna drive. So fault code 3055, which is the 64 megahertz clock failure, the first recommended action is to replace the TR1. So most probable cause, if only 3055 is logged and it's not associated with any other fault, replace the TR1. If that doesn't solve the problem, you probably have a 64 megahertz coaxial cable fault, replace the cable. And then the final action would be, if there's something really crazy going on internally with the RP1, then the last resort would be to change the RP1. Now, if the next fault code group, 3055, if it's associated with 3057, which means the TO clock failure along with the 48 megahertz failure, the problem is most likely with the 64 megahertz cable. And the second choice would be, if that doesn't solve the problem, the TR1. And then 3055 and 3716 replace the RP1, and second choice, the TR1. And the last code on this slide, 5049, is a nuisance fault. Never a cable issue, meaning between the TR1 and the RP1, because the RS-422 cable is the one I mentioned earlier, which connects between the TR1 and the GDM module in the DA1. In other words, that's internal. So do a self-test of the system, again, and if there is only a fault code 5049 and no other associated fault, ignore the fault. It's a nuisance fault. We may try to correct that in a future software version for the system, but right now it's considered to be a nuisance fault. However, if that fault code isn't just seen on one fault leg, but we see it again and again and again, flight leg to flight leg, then we probably do have an intermittent cable problem. We need to replace the DA1. That cable is not replaceable on the flight line. You need to replace the DA1 assembly. Okay, on our last slide of fault codes, again, these are primarily associated with 64 megahertz T0 clock. There's a fault code 3106, which again is a nuisance fault. This is associated with the control input to the RP1 from the control panel, called a display selection mismatch. And I see that constantly when we're doing the evaluations of the customer's retrieve fault code. Ignore it. It's a nuisance fault. And again, that may be possibly changed or eliminated in future versions of the RP software. But for now, ignore it. 5051, even if the RP1 is logged fault codes 3049, which is the IF fault, 3057 is the IF fault, and 3055 is the 64 megahertz clock fault, do not remove the RP1. The actual action is to replace the TR1, because that 5051 is a sensed fault within the TR1. It has nothing to do with the RP. And 5046, same idea. Even if I've logged the 3049, 3057, and 3055 on the RP1, the action is to replace the TR1. Do not replace the RP1. And then finally, 3042, problem is with the 64 megahertz cable, the clock cable, replace that. And as choice number 2, it would be the TR1, and as the last resort, very rarely, but replace the RP1. Now, this certainly is not the entire list of fault codes. As most of you know, if you've reviewed the line maintenance manuals, the purpose of this SIL was to immediately try to clarify the common cause codes for removals, which are mainly associated with the 48 megahertz IF and 64 megahertz clock cables. This letter, which is available now in TechPubs, D2017-12000040, is released, and you can review that as your official document and for additional details. The applicable byte code tables and the line maintenance manuals will be updated to synchronize with the SIL, and we're doing that with the discrepancy reports to TechPubs.